So here we have the second example of this topic, setting up a reaction table for a pH calculation with a common ion. I'll move through this second example a little bit more quickly than my first example, but as always, I have provided additional information in the first example from this topic. So the first thing we need to do to tackle this problem and fill out the reaction table is to write out the chemical reactions at play here. Now we have more than one chemical reaction this time. The reason is because we have two solutes in this solution. We have our weak acid, hydrocyanic acid, but we also have another solute, sodium cyanide, a strong electrolyte, ionic compound. So this first reaction will look like this. We have our weak acid, hydrocyanic acid, reacts with water, and the result of this reaction with water will be hydronium and cyanide. The reaction is balanced, so the stoichiometry is good. And if I look here closely, I have my acid, water is acting as a base here, and I end up with the conjugate acid of this base and the conjugate base of this acid. So let's look at the second chemical process that is at play here. We have also added this ionic compound, sodium cyanide, to solution. So it's already in the solution, so I'm just going to write it as aqueous. And so what does sodium cyanide as a strong electrolyte do when dissolved in water? It dissociates completely. That means that it breaks apart into sodium metal ion, hydrated with water molecules, and cyanide. If I check the stoichiometry of this reaction, it's also balanced. So in water, when this dissolves, I end up with sodium metal ion, but more importantly, I end up with this, cyanide. Well, where else do we see that? We see that here as a product from this reaction, the ionization of hydrocyanic acid. So that means that this is our common ion. And when we have a solution, whether it's acidic or basic, and we have a common ion effect at play, that means that the solution, in this case, because we have an acid, is going to end up being less acidic than it normally would be. Why? Because of this common ion effect and the increase in the concentration of cyanide, the equilibrium for this process is going to be shifted to the left. So we need to account for this because the final concentration of hydronium will be affected by this shift in equilibrium, which ultimately affects the pH. So let's determine our concentrations. We want to look at the initial concentration for hydrocyanic acid. Well, that's easy. It's given 0.36 molar. What will the change in concentration of hydrocyanic acid be as we move towards equilibrium? It'll be minus X. It will change by some small amount, and that small amount will be equal to the hydronium ion concentration. Well, what will the final concentration of hydrocyanic acid be? It will be 0.36 minus X. What about the initial concentration of cyanide? Well, in past topics, when we create our reaction tables, it's equal to 0 because we are only looking at this reaction in past topics. But now we have two reactions at play because this solution has two different solutes, this and this. So we do initially have some concentration of cyanide, and that concentration is equal to the concentration of the sodium cyanide in solution. That concentration is 0.45 And I know that the concentration of cyanide is equal to the concentration of sodium cyanide because of the stoichiometry, 1 and 1. Because this reaction goes all the way to completion, all the way from left to right, it's a unidirectional arrow, then the concentration of this would also be the concentration of this after the reaction has completed. The change in concentration would be X. The concentration of this will increase to some small degree because some of this will ionize, even though we do have the common ion effect in play. The final concentration will be 0.45 plus X. So to finish this up, the initial concentration of hydronium will be 0. Yes, we will end up with some hydronium produced, but initially there will be none. And that is simply because water will not react with this or this to produce hydronium. The change in concentration is equal to X here, and the final concentration of hydronium at equilibrium will be X. So if they did ask us to go one step further and calculate the pH of the solution, well, the pH would be equal to the negative log of the hydronium ion concentration, and you would get that from here, whatever X turned out to be.